The National Electrical Code outlines specific requirements for a 400 amp underground residential electrical service. These requirements address both conduit size and conductor size to ensure safe and reliable operation. Let's examine the details. Firstly, conduit size. The NEC mandates a minimum 3-inch conduit for single conduit installation. If using parallel conduits, the equivalent cross-sectional area must be maintained, as determined by Table 300.19d. Secondly, conductor size. For aluminum conductors, the NEC specifies a minimum of 3/0 American wire gauge. Now let's discuss why these requirements are in place. Using undersized conduit, for example 2-inch instead of 3-inch, can lead to several problems. 1. Insufficient space for conductors, which makes pulling the wires difficult and increases the risk of insulation damage during installation. 2. Inadequate bending radius. Sharp bends can stress the conductors and potentially damage them over time. 3. Overheating. A crowded conduit restricts airflow, which leads to heat buildup and reduced ampacity of the conductors. Using undersized conductors such as 4/0 American wire gauge aluminum and 3/0 American wire gauges required also poses risks. 1. Overheating. Smaller conductors cannot handle the 400 amp load without overheating, potentially damaging the insulation and creating a fire hazard. 2. Voltage drop. Undersized conductors cause excessive voltage drop, leading to inefficient operation of appliances and equipment. 3. Code violation. Using undersized conductors is a direct violation of the National Electrical Code and can result in failed inspections and potential fines. Therefore, it's crucial to upgrade the underground service to meet the minimum requirements. Replace the 2-inch conduits with 3-inch conduits or an equivalent parallel configuration. Replace the 4/0 American wire gauge aluminum conductors with 3/0 American wire gauge aluminum conductors. There are additional considerations to keep in mind. Always consult with the local authority having jurisdiction to ensure that the proposed changes meet their specific requirements and interpretations of the NEC. Obtain the necessary permits before commencing any electrical work. This ensures that the installation is inspected and approved. Engage a qualified electrician to perform the installation. A professional electrician has the knowledge and experience to perform the work safely and in accordance with all applicable codes and standards. Always prioritize safety when working with electricity. Energize the circuit before starting any work and use appropriate personal protective equipment. Let's go over some additional details regarding conduit fill and conductor ampacity. The National Electrical Code specifies the maximum allowable percentage of conduit fill. This percentage is based on the number of conductors in the conduit and the type of conduit. Exceeding the allowable fill can make it difficult to pull the conductors, damage the insulation, and reduce the ampacity of the conductors. When selecting conductors, it's crucial to consider their ampacity. Ampacity is the maximum amount of current a conductor can carry continuously without exceeding its temperature rating. The NEC provides ampacity tables for different types of conductors and installation conditions. Factors such as ambient temperature, number of conductors in a raceway, and burial depth can affect the ampacity of conductors. These factors require adjustments to the ampacity ratings listed in the tables. For underground installations, the NEC specifies minimum burial depths for different types of wiring methods. These depths protect the wiring from physical damage and ensure proper heat dissipation. It is important to consult the NEC tables to determine the appropriate burial depth for the specific installation. Grounding is a critical aspect of electrical safety. The NEC requires all electrical systems to be properly grounded to provide a low impedance path for fault current. This helps to protect against electrical shock and prevent damage to equipment. The grounding system consists of a grounding electrode conductor, and equipment grounding conductors. The grounding electrode is typically a ground rod, a metal water pipe, or a concrete encased electrode. The grounding electrode conductor connects the grounding electrode to the service equipment. Equipment grounding conductors provide a path for fault current from the equipment back to the service equipment. Bonding is another important aspect of electrical safety. Bonding involves connecting all metal parts of the electrical system together to create a common ground potential. This helps to prevent voltage differences between different metal parts, which can create a shock hazard. Bonding is typically accomplished by using bonding jumpers to connect metal enclosures, raceways, and equipment. Overcurrent protection is essential for protecting electrical circuits from overloads and short circuits. Overcurrent protection devices, such as circuit breakers and fuses, are designed to interrupt the flow of current when it exceeds a safe level. Circuit breakers are resettable devices that can be tripped manually or automatically. Fuses are one-time devices that must be replaced after they have blown. The NEC specifies the maximum allowable overcurrent protection for different types of circuits. Surge protection is important for protecting sensitive electronic equipment from voltage surges. Voltage surges can be caused by lightning strikes, power outages, and other electrical disturbances. Surge protection devices are designed to divert excess voltage away from the equipment, protecting it from damage. There are two main types of surge protection devices, which are whole-house surge protectors and point-of-use surge protectors. Whole-house surge protectors are installed at the service entrance to protect the entire electrical system. Point-of-use surge protectors are plugged into individual outlets to protect specific equipment. Arc fault circuit interrupters, or RSIs, are designed to protect against arc faults. Arc faults are dangerous electrical conditions that can cause fires. RSIs detect arc faults and interrupt the flow of current before a fire can start. The NEC requires RSIs to be installed in certain areas of the home, such as bedrooms and living rooms. Ground fault circuit interrupters, or GFCIs, are designed to protect against ground faults. Ground faults occur when current leaks from a circuit to ground. GFCIs detect ground faults and interrupt the flow of current before a person can be injured. The NEC requires GFCIs to be installed in certain areas of the home, such as bathrooms, kitchens, and outdoor areas. Electrical inspections are an important part of ensuring electrical safety. Electrical inspections are typically performed by local government inspectors. Electrical inspectors check to ensure that electrical installations comply with the NEC and other applicable codes. If an electrical installation does not meet code, the inspector will issue a correction notice. The homeowner or contractor must correct the deficiencies before the installation can be approved. Electrical permits are required for many types of electrical work. Electrical permits are typically obtained from the local government. Electrical permits help to ensure that electrical work is performed safely and in accordance with the NEC and other applicable codes. Before starting any electrical work, it is important to check with the local government to determine whether a permit is required. Working with electricity can be dangerous. It is important to take precautions to protect yourself from electrical shock. Always to energize the circuit before starting any work. Use insulated tools and wear appropriate personal protective equipment. If you are not comfortable working with electricity, hire a qualified electrician. Electrical codes and standards are constantly evolving. It is important to stay up to date on the latest changes to ensure that electrical installations are safe and compliant. The NEC is updated every 3 years. Local governments may also have their own electrical codes and standards. It is important to consult with the local authority having jurisdiction to determine the applicable codes and standards. Understanding voltage drop calculations is crucial for ensuring efficient and safe electrical systems. Voltage drop refers to the decrease in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can lead to reduced equipment performance, overheating, and even damage to electrical components. To calculate voltage drop, one must consider the conductor's length, current, and resistance. The formula for voltage drop is typically expressed as voltage drop equals current multiplied by resistance. The resistance of a conductor depends on its material, cross-sectional area, and temperature. The NEC provides tables that list the resistance of various conductors. It is important to keep voltage drop within acceptable limits. The NEC recommends that voltage drop should not exceed 3% for branch circuits and 5% for feeders. If the calculated voltage drop exceeds these limits, it may be necessary to increase the conductor size or shorten the conductor length. Understanding short-circuit current calculations is essential for selecting appropriate overcurrent protection devices. A short circuit occurs when there is an unintended connection between two conductors with different potentials. Short circuit currents can be very high and can cause severe damage to electrical equipment. To calculate short circuit current, one must consider the voltage, impedance of the circuit, and the transformer impedance. The formula for short circuit current is typically expressed as short circuit current equals voltage divided by impedance. The impedance of a circuit depends on the resistance and reactance of the conductors, transformers, and other components. The NEC provides tables that list the impedance of various components. It is important to select overcurrent protection devices that can safely interrupt the maximum short circuit current. If the overcurrent protection device is not properly sized, it may not be able to interrupt the short circuit current, which can lead to equipment damage and even fire. Understanding transformer sizing is crucial for ensuring that the electrical system can meet the load demands. A transformer is a device that transfers electrical energy from one circuit to another at a different voltage level. Transformers are used to step up or step down voltage to match the requirements of different equipment. To size a transformer, one must consider the total load connected to the transformer, the voltage requirements of the load, and the transformer's efficiency. The transformer must be sized to handle the maximum load without overheating. The NEC provides guidelines for transformer sizing. Understanding motor starting requirements is essential for ensuring that motors start and operate properly. Motors draw a large amount of current when they start. This inrush current can cause voltage drop and can damage the motor if it is not properly protected. To address motor starting requirements, one must consider the motor's horsepower, voltage, and starting method. Different starting methods, such as reduced voltage starters, can be used to limit the inrush current. The NEC provides guidelines for motor starting requirements. Understanding harmonics is important for maintaining power quality. Harmonics are distortions in the sinusoidal waveform of alternating current. Harmonics can be caused by nonlinear loads such as electronic devices and variable frequency drives. Harmonics can cause a variety of problems, including overheating of equipment, voltage distortion, and interference with communication systems. To mitigate harmonics, one must consider using harmonic filters and other power quality improvement devices. Understanding power factor correction is essential for improving the efficiency of electrical systems. Power factor is a measure of how effectively electrical power is being used. A low power factor indicates that a large portion of the current is being used to create reactive power, which does not do any useful work. Power factor correction involves adding capacitors to the electrical system to reduce the amount of reactive power. Improving the power factor can reduce energy consumption, improve voltage regulation, and increase the capacity of the electrical system. Understanding emergency power systems is crucial for ensuring that critical loads can continue to operate during a power outage. Emergency power systems typically consist of a generator, an automatic transfer switch, and a battery backup system. The generator provides power when a normal power source is interrupted. The automatic transfer switch automatically switches the load from the normal power source to the generator. The battery backup system provides power for a short period of time until the generator can start. The NEC provides guidelines for emergency power systems. Understanding renewable energy systems such as solar and wind power is becoming increasingly important. Renewable energy systems can provide a clean and sustainable source of power. Solar power systems convert sunlight into electricity using photovoltaic cells. Wind power systems convert wind energy into electricity using wind turbines. The NEC provides guidelines for renewable energy systems.